I'm going to talk to you about something that for some of you, you may have already seen some of before. This talk is really the full breadth of physical design, and it was originally presented in my 1996 book, but it's been updated for the next version. I wouldn't say version, I should say the next book, which is much larger in scope, and I've been working on for way too long. So I need to get it out, but this is definitely a key piece of that first volume of the next book. So the first thing I'm going to talk about is background material. It's not actually the levelization techniques, but the way in which we write software in terms of components, and I'm going to explain them. That's probably going to take about 40 minutes. So, but I think without doing that, the rest of it is kind of abstract. It's abstract anyway, but without seeing the concrete way we represent software at Bloomberg, then, well, it would be too abstract. So I'm going to do that. The next approximately hour and change is going to be the levelization techniques themselves. And then after that, I'm going to talk about insulation, which is an easier topic to talk about. There's lots of code in that one. And then finally, I'm going to show you how we compose components to solve a typical kind of business problem. That won't take very long at all, but it's a lot of slides, mostly like animation. So with that said, I'm going to start, and hopefully this is working. Please be working. I've got a what? Is it working now? Yep, okay. So I'll put this up, but don't worry about it, because that's just for the camera. And the abstract, again, is just for the camera. You guys have already decided to come here, so you'll see it. So I won't belabor that, but I'll leave it up for the camera for a second. And then we can talk about what the problem is. And this is sort of how I start out all of my lectures. This is a particular topic. It's one of many, many topics that together wind up being how we collectively write software in the core BD group at Bloomberg. And so there are many dimensions. And one of the things that I discovered, I guess, a long time ago is that there's logical design and physical design. Logical design is something that really is what's mostly taught in school, and physical design is the other stuff that isn't typically taught in school. And it requires us to be able to isolate, modularize our designs into discrete physical components. And that's a big deal, fine-grained physical components. We need to be able to express in English to human beings precisely what behavior these components provide, and then we somehow have to manage the physical dependencies that result from implementing that functionality. It can't depend on everything. Now, not everybody agrees with that. Sometimes people say, it doesn't matter what it depends on, it's an empty tale. In my opinion, after many, many years of doing this, that is the furthest thing from the truth that could possibly be stated in terms of maintainability. So that is the premise of levelization techniques. So if you completely disagree with me, you can either stay and be convinced, or you can say, you know what, that's nonsense, I have to leave. Hopefully you won't do that. And then finally, it requires attention to a number of different logical and physical rules that govern how we design software. And we're going to talk about more like techniques to help you improve rather than just following the rules. But the first part of this is to talk about some really hard rules. So the purpose of the talk is to review some basic design principles, and particularly with respect to components, and I'm putting this up here, component properties and logical diagrams, implementation, dependency, and level numbers. This was all covered in my first book many years ago. Two important physical design rules: when it's okay to collate public classes in the same component, our three-level aggregation strategy, and encapsulation versus physical insulation. So we'll talk about that a little later in the talk. When to include a header file or not, we'll talk about that a little later as well. Then we're going to introduce a variety of levelization and insulation techniques in that order, and how to avoid cycles in your designs, also excessive or otherwise inappropriate physical dependencies. So with that, this is the outline that I'm going to follow, and clearly 2 is the beef. 3 is a little more, and 4 will go quickly. It's just an application of some of the principles. Any questions? Good? Okay, so this is for all three. Oh yes, good question. All right, so review of elementary physical design. So we're talking about logical versus physical here, and when I represent a logical entity, I usually use an oval to indicate the logical part and a rectangle to indicate the physical part. That's just the iconography. So logical is classes and functions, and physical is files and libraries. And so here you see a bunch of components stacked nicely one atop another, and they form different levels of dependency, and each one contains some logical content. Each component that we write, except for the file that holds main, looks like this. It has an implementation file, the .cpp file, it has a header file, and it has a component level test driver. Test driver is used to exercise the functionality within that component. We're not going to be talking about testing today. That is a separate talk. Very interesting stuff. Unfortunately, it rests in the third volume, which is where I started many years ago, and I finally will wind up, hopefully not too long from now. All right, this is our fundamental unit of design, and it's not just a .h.cpp pair. It has 4 fundamental properties. So in addition to being a .h.cpp pair, it has these 4 properties. And the first of them is that the .cpp file of a component includes the .h file as the first substantive line of code. Can anybody tell me why it needs to be the first line? Why the first line? Why can't it be later? The H is independent of any other file. It's independent. Okay, so the point is that the .h file needs to compile in isolation. If you do what I just said, you'll never have include order dependencies, because when you go to compile and test this component, if the header file requires other header files in front of it, it won't compile. And then the client won't be surprised when your code works and the client's code doesn't compile. So this is an important thing. And so we always do this, and we do this even if the CPP file would otherwise be empty. This is just what we do. But besides all the other good reasons, the amount of time we could argue about whether we should have a CPP file or not for any given component dwarfs any value that you might think you'd get from leaving the .cpp file out. So this is what we do. So each component has a .h and a .cpp, and the header file is included as the first substantive line of code. Okay, the next one is quite a bit harder. All logical constructs having external linkage defined in a .cpp file are declared in the corresponding .h file. What does that mean? Well, first of all, we have logical constructs with external linkage. Before I explain that, we need to notice or understand the difference between defined and declared. So declared means introducing a name into a scope. Defined means providing the space or otherwise describing the definition, which can appear only once, ODR-wise, in the program. So what this is saying, in a nutshell, I have to explain external linkage. So external linkage, linkage is something that pertains to whether 2 declarations in separate translation units can refer to the same object. If an object has external linkage, they can. If it has internal linkage, they cannot. So that's what linkage means. So when we put it all together, all logical constructs having external linkage, meaning that they can be seen outside of the translation unit, that they can refer to an object outside of the translation unit more precisely, then if they're defined in the CPP file, they have to be declared somewhere in the header file. And the reason for this rule is we don't want to have ABI leakage out into the public world. We want to make sure that if there is some symbol that's creeping out of the CPP file of our component, that at the human readable level, there's a way to see that. So it could be declared private, it could be declared public, it doesn't really matter in the header file, but it needs to be declared. So that's that one. Now, the next one, all constructs having external or dual bindage. Now, bindage is a word that I made up because linkage was already taken. but it still seems to serve the purpose. I'll explain in a minute. All constructs having external or dual bindage declared in a .h file, if defined at all, are defined within that component. So I really do need to explain what I mean by bindage. If something has internal bindage, it is any use of a symbol, any use of a name, and the associated definition are handled by the compiler. The binding of the use and the definition are handled by the compiler. If it has external bindage, that binding is always handled by the linker. And if it has dual bindage, it might be handled by either. So what's an example of external bindage? A global variable, for example, int I semicolon. That has external bindage. I say extern int I in a separate translation unit. Somebody uses that declaration, and then at link time, the two are joined by the linker. Same thing for plain old C-style functions. Same thing for member functions that aren't inline. And so those have external bindage. Internal bindage things are like type defs and class declaration versus definition. Those are handled by the compiler, the association. Then there are two constructs in C++ that have dual bindage. And I mentioned one, it's inline functions. They have dual bindage. They could be inlined, in which case the compiler takes care of it, or the compiler could choose not to, in which case the linker will take care of it. Can anybody name the other construct in C++? Templates, exactly. This is good. This is great, because when I give these kinds of talks at my own work, people are a little bit less quick to just blurt it out. So if you can answer quickly, we'll get out of here sooner. It's awesome. I appreciate that. All right, so what this is saying is, since it says external or dual bindage, you must define it in the same component as you declared it. Another way of saying that is the only place you can have a forward declaration is when it's internal bindage. You can't have a local declaration of something that has external or dual bindage. So what that means is I can say class foo, that's okay, but I cannot say void f open close semicolon. That's not allowed unless I've defined void f open curly close curly in the CPP file or as an inline function down below the class. Does that make sense? Okay. Now, there's a good reason for this. I need to have a place where I know this thing is defined just by looking at the header file. I need to be able to say, this component defines this logical entity. And if that isn't unique, if that isn't fixed, then I can't really draw a graph because I have no idea what the nodes mean. So that's an important property. And the fourth one is a component's functionality is accessed via and pound include of its header file. We've already established that that's possible. And never via a forward extern declaration. Use the word extern because I'm really talking about things that are handled or potentially handled by the linker. Okay? So I'm never going to make a local declaration of something that is ever handled by the linker. I am always going to pound include the header file that is required to declare it. They all fit together. The really good thing about this is I no longer have to parse C++ to know what my dependency graph is going to look like because the pound includes themselves form an envelope of allowed dependencies. And so by looking at them with a Perl script, not Clang, didn't have Clang 25 years ago, I can very quickly determine the envelope of physical dependencies in my system. This is a great thing. This is a huge property. I can't stress it enough. That's really the reason. The other reason, which is just an, oh, by the way, you don't get stupid breakage when you change the definition of something and forgot to change its local declaration somewhere. You know, you get some strange things. If this were C, you could get a runtime error. In C++, it typically, especially with functions, a link time error, but not necessarily when you're dealing with variables. Not that we would ever have global variables, but just saying. All right, so any questions on that's the hardest, by the way, that is probably the hardest thing, yes?
How do you enforce this?
Okay, so the question is, how do I enforce that people do this? I have a flail on my desk. I do. I absolutely do. And if anybody were to deliberately do something other than this under anywhere near me, I would immediately pick up the flail and walk over to their desk. We also have something called BDE Verify that we've been working on for over 2 years. It's a Clang-based tool and it guarantees all of these silly rules. So that's the other answer. But I like the flail better. Okay. Yes? Okay, so the question is, what do we do with templates and inline functions? Templates and inline functions have dual bindage. Since they have the possibility of being handled by the linker, they are not allowed to be forward declared. They need to be defined in the same component in which their declaration occurs. Put another way, you can't declare them in another place in addition to the one where they live. Where they live is where they live, and you need to have that. Otherwise, you can't draw meaningful graphs and talk about where the definition is. This is important. This is like core stuff, okay? Yes? We use forward declarations for classes. And there are pros to that. Used to be much larger than they are now. And there are cons to that. It's harder to re-engineer code if you don't have a single repository the way Google does. And we don't have a single repository. And so what we need to do is a little bit more onerous when we go to re-engineer things if we have to go change all of our clients, which we don't have access to. So there's an upside and a downside. The upside is if we make a change to the class definition, our clients don't have to recompile, and we're going to see that in section 3. So there is an upside to that as well. And we'll talk about that as we go. All right, so I've drawn this pedagogical diagram here. We wouldn't really have a value semantic type like polygon inheriting from an abstract shape because it's not very meaningful. But still, I want to appeal to your intuition. So shape is an abstract class. Polygon is concrete. Polygon uses points in its interface. What does it mean to use something in its interface? Well, if I have a function that takes something in its signature, a type, or returns it as a return type, then we say that it's used in the interface because you can see it programmatically, it's there. If I have something, if I have a class that uses another class in its interface, it means one of the member functions of that first class uses the other class in its interface. So that's really all it means. Now, their other thing is I might possibly use something not in the interface, but still use it substantively in the implementation. So if I use it in the implementation, but not in the interface, that's another kind of using. And then, of course, there's ISA, which is a polygon, public interface, inheriting from shape. So those are the 3 things that are key, and then there's one funny one. We'll get to that in a minute. So let's start with this. ISA. A polygon is a shape. And so we just draw this picture. You notice it's bubble to bubble. So we have a polygon is a shape because that's a logical relationship. Next, we have uses in the interface, which I just described. And polygon uses point in its interface, for example, to add a vertex. So we have this symbol. The bubble is on the polygon. It's a clear bubble. That means it's used in the interface. All right? Then point list and point list link both use point in the interface. Now, you'll notice that point list link has an underscore. That means that point list link is not allowed to be used outside of the component in which it's defined. You could think of it as being a nested class of the component. We don't do nested classes of a class because it creates extra levels of hierarchy that are not useful for our describing logical relationships or physical dependencies. So this is the way we do it. This again is enforced by our tools. And it's something that we started a very long time ago when nested classes weren't really supported the way they should be. And even now we find this better. So this is the way we do it. There is a mapping from this to a nested class, but you lose certain things by doing it. This is better, strictly better. But anyway, so both of these, the point list and the point list link, use point in their respective interfaces. So hence you see the diagram. And then we have uses in the implementation. And a polygon is implemented by embedding a data member of type point list in it. So polygon uses point list in the implementation. But you wouldn't know that programmatically because there's no interface part of Polygon that exposes a point list in it. By the same token, there's nothing in point list that exposes a point list link in it. Okay? So we have that. So far, so good? Question?
Could you define a component more precisely?
Okay, a component is a .h.cpp file having the same root name with the 4 properties that I described. You remember the includes, it's in the CPP, it's declared in the H. If it's declared in the H, then unless it's a internal bindage, then it is defined in the CPP. Okay, and then finally, if you use it substantively, you include it. Those are the 4 properties. That is what we define to be a component. Okay, if it's not that, it's not a component. If it's that, that doesn't mean it's a good component. It's just at least a component. Okay. Okay. All right. And then there's this last one, and this one is hard to get your mind around, and you may not even believe me when I tell you, but it turns out that it's possible for a component to use another component in its interface in name only. And what in name only means is that you don't have to include that component to compile, link, and test the component under test. And shape is an example. Shape uses point in its interface in name only. Okay? This does not happen in nature unless you make it happen, except for abstract interfaces. So if you have an abstract interface, then this will happen. And for example, shape may have a get origin function. We would just say origin, but the idea is it's going to return the origin of the shape. And it can do so by forward declaring class point without ever including point anywhere in the component, even though the shape returns a point by value. If this is shocking to you, excellent. Go try it. The other thing is, if shape were concrete, but used a forward class declaration for point, the include would not be in the header file. Even though it's returning a point by value, the include would be in the .cpp file. So this is interesting compile time stuff that's worth trying and getting a handle on, because where you put the includes matter, and what allows you to put the include in the CPP is the forward declaration of the class. Okay? Yes? Okay, so uses in name only means I have shape. It says it uses point in name only. That means I don't need to ever include point. I never need to see its definition. I don't care. And I can compile, link, and test shape in isolation. Yes?
You said it's possible to have shape returned by value?
Yes.
If you do in the CPP. So what if I want to maybe call size of the return value of the function only including the header file?
Okay, so the question is, what if I want to call size of the return value of the function? When you use point, when you call the function that where you actually need to use point, you have to include it yourself. Right. Okay? Yes.
Can I just test my understanding of this?
Sure.
If shape had a concrete method that took a point by reference, that would be a regular old use in the interface. But if it had an abstract method that took a point by reference.
Okay, so I understand the question. The question is this. Suppose I have a function that takes a point by reference in the interface, right? It uses point by reference in the interface. But the function is implemented in the CPP file. All you need is class point in the header file. But you need to include it in the CPP file, because it's using it substantively. In the header file, it doesn't need to know the size.
So does that count as name only, or does that count as interface?
No, that's uses in the interface. It doesn't matter whether it's an inline function or whether it's a non-inline function. It uses it in the interface, and you must include it in the component. It's only when you don't need to include it anywhere in that component or any component on which it depends, when it's truly used in name only. And I'll explain that even a little bit more in just 1 second. This is, I know it's hard. That's why we need to go through this a little bit. Otherwise, what I would be saying next would be absolutely crazy. It still is. All right, so the next thing is depends on. And depends on is a physical relationship. It's not a logical relationship, and it goes from box to box. If polygon uses shape if polygon is a shape, then that's the strongest kind of logical relationship. It's a compile-time physical dependency, and so it implies this depends on relationship between the component that defines polygon and the component that defines shape. Okay? That's called an implied dependency. As soon as I know that there's an is-a relationship across component boundaries, that's 100%. Okay? Then I have the uses in the interface from polygon to point. And so that implies a physical dependency. So if I use something but it's not in name only, there's another physical dependency. And of course, point list and point list link both imply a physical dependency. Can anybody guess where the last physical dependency is? There you go. So this is what implied physical dependency is. Once you have your logical relationships, which are an abstraction on the actual interfaces of the components, then you, and also knowing the data members, of course, then you can infer physical dependencies, and that's a higher level of abstraction still. Once you have that, we can go to level numbers. And this is where I hope it will tie down the difference between uses in the interface and uses in name only. So something in this, at least one component in any subsystem has to be at level 1, right? The one that doesn't depend on anything else. So there could be more than one. So what for sure doesn't depend on anything else here? Okay, I heard shape, but did anybody think point? Okay, so point for sure. But because of what I said about the includes, it's also shape. So these two are at level 1. Even though shape looks like it depends on point because it has this nice dotted line, it's collaborative dependency, it's not a physical dependency, and so it's in name only. It does not affect level numbers. Anybody want to guess which component is at level 2? Okay, pointless. So you guys are getting this, right? There's one left. What is it at? Level 2 or what? Okay, good. So we're good with this, right? This makes sense. It's old stuff. So this is called a component class diagram with level numbers, and it also shows the physical dependencies. So this you can do to any design. If you wind up with a design that has the big black arrows pointing this way or causes some crazy cycle, then you know you have a design problem. And the second part of the talk is going to help you through that. All right, so essential physical design rules. We have two essential ones. I mean, we're talking like big ticket. If you break these, forget about it. Okay, the first one, guess what it is? There you go. That's the first one. The second one is a little more subtle, but it's important. And anybody want to take a shot? There you go. Somebody read my book. No long-distance friendships. It's not that you can't have friendship. That is perfectly fine, but you can't cross a component boundary. Because as soon as you do that, you allow the possibility of checking out a separate physical entity, let's say a list, and if say you had a cursor that's allowed to change the list, you check out the list, you add a tail pointer, you put it back in, and at some later time, you build the system and the cursor doesn't know about the tail pointer, and it just everything goes to hell in a handbasket. So you don't want to do that. You want to make sure that everything that has private access lives within the same physical boundary. Another way of saying that is the logical unit of encapsulation should be nested within a physical unit of encapsulation. And this, by the way, goes to the notion of logical physical coherence. You want your logic and your physicality to be coherent and not separate. Like my logic is here, here, and here, and my physical part is here, here, and here. No good. They have to be one and the same. Hope that made sense. Yes? We can say that friendship is allowed only within the same component. We are saying that. That is a very good way to say it. Love it. All right. Okay, so criteria for co-locating public classes. We saw that that thing with the underscore was co-located in the same class as the point list, but it's a private class. So, or it's component local. It's not allowed to leak out. What if we have more than one class that can be used externally in a component? Under what circumstances might we consider doing that? Well, you said what? Okay, that's very infrequently. We try not to do that ever, even within the same component. But there's one thing that we do regularly when we need to. What is it? No. No. But you should get the answer. The first one is friendship. If we need friendship across two classes within the same component, for example, an iterator. If we put the iterator not nested within the class, but let's say we put it ahead of the class, then it grants friendship to the container, then it's perfectly okay to use the iterator and the container, and life is good, and the container has private access to the iterator so it can construct it as needed. Everything's fine. Make sense? Okay. So friendship is the number one reason. Yes? That is the fourth reason, but we don't call it flyweight. We call it something much more descriptive. Absolutely not inheritance. Most likely no. Any ideas? Okay. Well, anyway, I will tell you that although the cyclic dependency thing is there, we try not to do it. Even though it would be allowed, the typical way of implementing, as I understand it, I don't know how everybody does it, of implementing a container iterator pattern is to have the iterator nested within the container, and I don't want to do that. So I want to put the iterator ahead of the container, but unfortunately the iterator would then have to know about the guts of the container. So what we'll do is we'll actually use a levelization technique and put the guts as its own class before the iterator. So we have the guts, the iterator, and the container depends on the iterator and the guts, and the iterator depends on the guts. And it's acyclic, and it's beautiful, and you can build it up and understand it without having to go back and forth and wonder what the incestuous relationship is between nested classes. So anyway, the third one is a single solution. Now with C++11, we don't really need this anymore, but this is not a C++ only talk because this is architecture. And this applies to any language that has multiple translation units. So here's an example. If I don't have a variadic template or macro mechanism, and I need to have multiple entities that together do the same thing as a variadic template or a variadic macro, then I can put them in the same component, and it's okay, because putting them in separate components would be madness, would do nothing good. It would simply scatter, you have to include 7 things to get something to work. So that's not the point. The point is it solves one thing, okay? Here's an example of what not to do. Here I have, let's say I have at the lowest level, I have a coordinate. Then the next level, I have a point. The next level is a box. The next level is a box collection. And the final level is a garage. Got these 5 things. Now you might say, John, how could I possibly use a box collection without a box? That makes no sense. But that is not what you ask. You say, could I use a box without a box collection? The answer is yes. So for that reason, this is a bad idea. And what we're going to do is we're going to take the coordinate and make it its own entity. And anybody who wants to use a coordinate is free from any dependencies on these higher level things, and so on and so forth until I get to the garage. And if I need the garage, I need the rest. But at any point, I can cut off the stuff above and use it independently. Do you see the point here? Fine grain reuse. Very important. That is another talk, but very important. Questions on this? Okay, good. So this is fine. Now finally, what was it? Flyweight was suggested. The next one has this descriptive term, which is flea on an elephant. See? Now, flyweight, what does flea on an elephant mean? Well, I'll explain. So if you have something like a logger and you have a scope guard that is used to initialize the logger in main and then get rid of it, well, that's fine. We'll let you do that. Even though it's technically 2 classes, the scope guard is a flea, right? It's just a little bit of sugar. Whereas the elephant is a big thing. Now, if you go the other direction, then you have an elephant on a flea, and I might want to use my flea, but the flea would definitely notice if an elephant were on it. So this is a bad idea. We don't want to do that kind of thing. Now, I do have to say that people can abuse these things, where they say something that isn't a flea on an elephant is a flea on an elephant, like a goat on a pig or something like that. We don't do any of those things, right? No ducks on cows even. No, just flea on an elephant, that's it. And be careful not to rationalize that it's something different when it's not. Okay, so now we've seen these levels of dependency, but they're only one level of aggregation. Components are the first level of physical aggregation, and they have logical content, but we need more than that. And there is no such thing in the C++ language yet, and modules, I'm hoping someday, will serve as the second level of physical aggregation, to be determined, but I hope, going on record. In any event, we have them now, we call them packages. And a package is a collection of components. And we don't extract the dependencies among packages to define them. We specify them explicitly. So this higher level package is allowed to depend on the two lower level packages, and that's it. What do I mean by depend on it? I mean a component within the higher level package is allowed to depend on any component within a lower level package on which it's allowed to depend. Now, question, why is it we specify this extra data that has nothing to do with C++ rather than using tools that just extract the includes, as I said we could, and figure out what the dependencies are? To make it hard to introduce, make it hard to introduce dependencies that we didn't want. Okay, so that's exactly right. We want to do that. That's a good answer. But how about this one? What if we're just designing the system? Does anybody ever design a system before they write the code? Ever? What if you haven't actually gotten any components yet? You're in the process of designing the system, and you'd like to have a physical design specification for what the higher level architecture is going to look like. How are you going to extract anything from that? Then your point is, as we go along, maybe we deviate from this process and get something wrong. And then our tools, which of course detect this, because now we use the extraction mechanism, which we can do because we follow the component properties, and therefore we can extract them instantly as we build our stuff. This great stuff. We find out we did something wrong, we get an error. Make sense? This is old technology. This is literally 20 years old. All right. Now, we can create a hierarchy of the second level of aggregation known as packages. Okay, so here we have it. And we can actually take it further. We're going to have package groups. Package groups are, guess what, a group of packages. And you can say, well, really? Do I really need components, packages, and package groups? Yes, you do. Packages are unique, have a name that's unique throughout the enterprise, but they're too small to be units of release in most cases. You want a unit of release that's substantial. And the unit of release, if you think about it like this, a package group is like a continent. And a package is like a country. And there are many countries on the continent, but they don't necessarily speak the same language, use the same currency, or anything like that. They simply reside on the same landmass, i.e. the same level in the enterprise-wide physical hierarchy. So that's what we call a package group. And the three are important. We'll now look at something else. They're also regular. What I'm showing here now is a packaging system where we could have just a component or a package, or we could have a combination of component, package, and package group, and so on. And we could keep going up the line, and you can see that it's really not very readable. It's hard to compare something that's really small with something that's really large, right? So it's better to have a bunch of small things that roll up into something that's medium-sized and a bunch of medium-sized things that roll up into something that's large, and that large thing is your unit of release. That's the idea. And this turns out to be much more approachable. Now, turns out I tried to write my book this way so that I would have chapters, I would have volumes, which were the big things. And then I would have chapters, which were the medium-sized things. Then I would have sections, which are the small things. But it turns out the sections are really not at all close to the same length. And they vary so widely that it turned out that I might not be a good metaphor, although it was a thought maybe 15 years ago. It's just not a good idea. So I'm going to wind up having to introduce an extra level in my book. It kills me, but when you have a section that's 5,000 lines, it's a little painful. So have to do a little better there. But it does work for software, and the constraint is that you want components to be more or less the same size. More or less, and the definition of that is, can it be tested from a single test driver? And if the answer is no, you got to do something. And there are a lot of things we can do with that. All right. So this is a bad idea. Instead, we're going to have a component package and package group, and it's exactly 3 levels of aggregation. It also admits a very nice naming scheme. We'll omit that for now. And then our units of release are going to be packages and package groups. Now we have this other thing, which is this package group hierarchy, but the way we're going to implement that is we're going to deal with it as separate package groups that have their own dependencies on other units of release. So this is the way we deal with our packaging and so on. So exactly 3 levels of aggregation. And with that, does anybody have any questions? Because we're done with the first part, and I'm 2 minutes over what I was hoping for.
Are we at the part where we can start drawing the system boundaries and where shared resources can reside by the time we're at the package hierarchy?
Okay, I think the question is at the package level, can we start dealing with system boundaries? And I'm not sure what you mean by a system boundary. I'll give you an example. Suppose we change vocabulary types. We're using our own custom string for whatever reason. We want to go to std string. So that would be a kind of boundary where we do a translation.
Or a shared third-party library.
Right, absolutely. So a shared third-party library would most likely be a package group or a big unit of release boundary. A package is typically within another package group. You can have standalone packages, but the trouble is it's hard to keep track of lots of little things. If you imagine something the size of a Google or Bloomberg, how many packages there would be. Even package groups, it's huge. But there's also something to be said for grouping your packages based on their dependencies so you can find things and so you can have reasonable dependencies, right? So yes, package group I think is what a third-party library would correspond to, but it doesn't follow the internal structure. It's in a regular unit of release for us. Any other questions? Yes. Oh, yes.
What is the interface of this package? Is it out of those components interfaces and the interface of this package, or you somehow specify the interface for this package?
Okay, I think I understand the question. What makes a package a package? So the answer is a package shares a common prefix. In the medieval times, before there were namespaces, what we used is a logical package prefix, and then we had a physical package prefix. That was preceded by an underscore. Now, when namespaces came into being after much resistance, because I really liked the way it was done before, because I was used to it, I realized that there's really no harm with the logical prefix of turning it into a logical namespace. So everything within a single namespace or physical prefix is a package. They're grouped together and they're put into typically into a single header directory during development. Now, how you deploy it is different. When you roll it up into a unit of release at the group level, you put all the different package headers into a single unit of release directory, perhaps, or even possibly combine more, but that's a deployment issue. But the idea is that everything within a package shares a common enterprise-wide unique prefix. And it's represented logically as a namespace and physically as package name underscore. Does that make sense? Okay, so I understand the question now. You should design, if you're trying to get hierarchical reuse, you don't want to hide, and we'll explain this, you don't want to hide components from users. You want to hide the use of components from users. So maybe I write something that has to do with the Gregorian calendar, and it's perfect. But then I change my implementation of date to the proleptic Gregorian calendar. But the Gregorian calendar component is just fine. I just don't use it anymore. So what I want to do is I want to allow people who used it before to continue to use it, but I don't want people in date. This is a little bit of a bad example because it actually affects the contract of date in a very evil way. So that's not really a great example. It doesn't hurt anybody who's, in modern times, but people who were trying to calculate bonds in the 6th century are going to have a problem. So you see what I'm saying. It's just an example. So we're going to talk about that, but a package is really nothing more than a collection of components. And with very few exceptions, all of the components are available for external use, and there is a mechanism to stop that, but it should be used only sparingly because it defeats the purpose of hierarchical reuse, which is one of the goals of what we're doing here through fine-grained modularity. You don't want to keep our implementations to ourselves. We do want to make sure that if we change our implementations, we don't hurt anybody, but we don't want to hide them. We want to hide their use. That's a good point. Yes? How do we separate our component hierarchy by packages? Okay, so the answer to that is we want to put components with the same dependencies, first of all, in the same package, and we want to put components that make sense semantically, not syntactically, but semantically in the same package.
Then you said something about the top level of one package depends on the bottom level of another package. I got it correct.
The top level of one package, that's interesting, depends on the bottom level of the other. No, I think it would be, you have a package, you have another package. If you allow a package to depend on another package, you're saying any component in the higher level package can depend on any component in the lower level package. Okay. Oh boy. Yes?
Organizationally, when people are working on these packages, do you tend to see like this team works on this package and this team works on this package? Or could a person be working on lots of different?
Okay, depending on the level, if it's a very low level package, say I have a collection of allocators. Have allocators being worked on by different teams and given to a team that's responsible for managing. Typically, there's somebody who's the package owner, but you can have submissions from a lot of different people. Then there are people that are doing their own application. They have an entire package group that they're using to design their app. So it's an application level package group, and so they'll do that. Okay. Yes.
Probably statement cyclical dependencies between components should be avoided, but they should be avoided between packages and packages.
Absolutely. The higher up you go, the bigger the deal. Yes.
So when you were talking about the organization at level 2, level 3, level 4, as you put these things together, you had that slide showing how they could all mix together and said that was bad, correct? You want to have them all.
Right. I'm saying that having them all mixed, in other words, when you're statically creating a collection of components, you want them to roll up into a package that has a purpose that people can grok, right? You don't want to have, in addition, a package group here and then a component here and say I have this other thing here that rolls up a package group and a component, because that doesn't allow you to recursively descend at roughly equal levels of complexity. That's what I'm saying.
So ideally, you'd like them all to be roughly the same size going all the way down.
Roughly. But it's not necessary. The components are the ones that really need to be like the same size pebbles. But it's not going to kill anybody if you have 50 components in a package group, and then this one has only 15. That's okay, because it's really, the idea is you want to try to compare apples with apples. Even if this apple is bigger than this apple, it's still an apple. It's not a truck of apples.
So the thing that smells like to me, that I hope, you may answer this later on, in which case don't answer it now, but when I hear that, I think of the utils module and chapter 8 grab bag, and where people will just dump things into.
Okay, so let me explain that. The difference between the dump things in model and what we do is you have a bunch of application developers and they find something they think is cool and they throw it into the demilitarized zone, DMZ. This goes in there. No one's maintaining it, it's just there. People can use it and whatever. And that turns out to be, as you say, a grab bag. That is not what we do. We do just the opposite. People offer things to us and we curate it into a very carefully crafted lattice of useful stuff that satisfies our level of quality. It is the opposite of what you just said. What you just said is not effective.
I definitely know it's not.
I'm agreeing with you. It's not, does not work. What we do does work. It's the opposite though. We receive it and we put it into place, or we write it ourselves. But we do not let people put it there.
I'm saying I've never worked a place that didn't have the one util directory.
We don't have it. We absolutely do not have it. There is no such thing. And I agree with you. Remember I'm agreeing with you? But I knew this 20 years ago, and I would have agreed with you then. And I still agree with you. I'll probably agree with you until the day I die. Okay? Oh, and just to mention the previous question was about it's bad to have cycles at the package and at the package group level, right? And the answer is absolutely even more so. All right. Okay, dumping is not allowed. There's no dumping here. If anybody wants to just read these questions, yes.
What if there are like many applications that just need a single component? They are forced to include the whole package. Isn't a possible disadvantage increasing compilation time because you're forcing to include the entire package?
Okay, the question is, you might be forced to include the entire package. If that's a problem, then there are things called insulating wrappers that you can create, okay? And that is a topic of Section 3, okay? All right, at the risk, all right, last question.
Yeah, in the case of templates or inline functions, does your model support splitting the definition and declaration in two separate header files?
No. One of the things that we want to do is, first of all, I don't see the advantage because we're not hiding anything from the compiler. We're just pretending to hide it from the human being. What we do is we have the upper part and the lower part, and it says inline function definitions down here. So you can go look down there, but they're not inline. They're below. We never put the inline definitions at that point. All right. A lot of good questions. I'm worried, though, that if I don't keep going, I'm going to get behind to an extent where I can't finish. So even though we have only 5 minutes, because we had a lot of questions, I want to continue just starting on the next one, but we're going to break right on time. So here are some things that you might want to just look at for yourselves, make sure you understand. But in particular, can anybody remember how we do this? What is it that allows us to do this? We have a single header that represents the component, but that's true of a lot of places do that. But what's true about that allows us to extract the component dependencies efficiently? I mentioned it. Does anybody remember? The list of the includes, but there was a property. Important. All of the properties add up to this, but the fourth property that says if you use it directly, you include it directly, you don't declare it locally, the link one, that's what makes sure that we have covered the envelope of physical dependencies. Otherwise, you could possibly have a local declaration that allows a physical dependency to slip out without knowing that you have it, and then you can calculate all your include, get your solution, go to link it, and realize you're missing a linker symbol. So that's why this is important. I just wanted to bring this out. The properties are important. All right, we have 4 minutes left. I'm literally going to start the next one and stop like on the third slide, but I really want to keep going because I think you should. Okay, so here we go. So levelization. This is a horrible word that I made up a long time ago, but it actually has a meaning, and I want to just let you know what it is because this is what we're going to be talking about. Levelize. It's a verb. We need to levelize that design, i.e. we need to make its physical dependency graph acyclic or levelizable. Are you sure that design is levelizable, i.e. do we know how to make its physical dependencies acyclic? Levelization. What levelization techniques would you use, i.e. what techniques would you use to levelize your design? So this is my shameless advertisement for my 1996 book and the one that's coming out shortly. And I happen to be working on this specific section back in my hotel room when I'm not out here talking or partying or whatever else I do. Anyway, there are 9 techniques that are originally described back in 1996. And it turns out that they're pretty much the same, but there have been some new incarnations of them. In other words, new ways to implement the basic idea. So we're going to learn these now, and we'll apply them later to real-world examples. And with the last minute, I'm going to do the first one, which is called escalation, moving mutually dependent functionality higher in the physical hierarchy. And here we have an example of a rectangle and a box, and the two are mutually dependent. They both depend on point. So if you look at the rectangle, you'll see that it includes point and box, and you'll see box includes point and rectangle. That's a bad thing. The reason they do it is because there are conversions, mutual conversions. This is the interface, but anyway. So this is the. Let me go back. Sorry. This is not the interface. These are the data members. They're slightly different. They have different performance characteristics. This is the interface, the public interface. And you'll see that they're slightly different as well. And you'll notice that these are implicit conversion operators, right? Constructors, I'm sorry, not operators, constructors. And so this cyclic dependency is very harsh. It's in the interface as is. There's nothing we can do to fix this. Now, you'll notice that there are include box and include rectangle. And some people believe that just by removing the includes and replacing them with a forward class declaration, that they've done something. And they have done something. They've reduced the compile time coupling, but they have not eliminated the physical dependency. It's still there. Okay? This is no good. So, we have a diagram that looks like this. This is bad, right? We know this is bad. We have to fix it somehow. One way we could do this is we could escalate box above rectangle. And that would look like this. What we've done is we've said that box depends on rectangle. That's good. And we put in both a constructor that takes a rectangle and a conversion operator that takes it to a rectangle. Now, I'm not suggesting we actually do this, but I'm saying this is a technique that you can use. Make sure that box knows about rectangle, but not vice versa, and you get this diagram. And now the problem is, the way we've done it right now, if anything in rectangle.h changes, all clients of box need to recompile because we included box, a rectangle, in the header file of box. Now I'm mixing two things. I'm mixing compile time coupling and physical dependency. That's okay. Let's do it the other way. This time we're just going to have a forward class declaration of box. So look here, it's just class box. Now we have the same physical design, except that if something changes in box, the clients of rectangle are not affected, just the direct clients of box. So the best thing we can do is take everything out of box and rectangle that is mutually dependent and escalate that to a higher level convert util. And so now we have something that looks like this, and we have rectangle.h and box.h included in the convert util because we're going to need to avoid, we're going to need to support inline functions, sorry. And then more on that later. This one, though, we include point here because we want to avoid what we call transitive includes. We don't want someone else's header file to include point when we use it ourselves. And here's an example of where we're going to be using it ourselves in this convert function, right? Box to rectangle looks like this, okay? The details aren't important, just the idea that it uses it is all that matters. All right, so now suppose we took this out. Then imagine later we decide we don't want to use the includes in the box and rectangle. We're going to replace them with class point. If we were to do that, it shouldn't break anybody, but because we took the include out of the top level one, now it no longer compiles. So we don't do that. We put it back in, and now it compiles again. And we're back to this thing, and the finer grain look at what we mean when we talk about this is this. This is just the physical dependencies excluding, this is file level physical dependencies and component level physical dependencies, excluding the logical relationships. So with that, I'm going to stop. If there's any discussion, anybody wants to talk about it, we're taking our break. What do we have, 15 minutes? You're dismissed. 15 minutes. We'll start on time.